We also cannot talk about values in a scientific course without talking about significant figures. Now, if you prefer to have information like this just as a list of rules that you follow and you can read, you do not have to watch this video. The rules will be the same as the reading linked on Canvas, or if this video survives somewhere in the far future where we're not using Canvas, it's on whatever learning management system we happen to be using. I am going to give the rules and walk through them in this video, but if you would like to just read the rules on your own, please refer to the ones that are linked on Canvas. Okay, so I have a picture here for us to look at to talk about uncertainty in measurement, which is really where we're getting all of our numbers from. So if you were measuring some volume, we can tell that it's a volume because we've got a milliliter here. So a liter is another way to talk about volume. And in the last video, we only brought up cubic meters, but we also use liter as a base unit for volume. And this graduated cylinder, which is one of the ways that we measure volume in a lab setting, has marks on it, right, to mark volume points. And if we zoom in on what this looks like, our water is, well, I'm assuming this is water. It's some kind of blue liquid, which is usually how they represent water. It's in between two of the markings. So we have to make some kind of guess. That'll be an educated guess, but it's still limited in terms of exactly how accurate that measurement is. So the point of this picture is just a demonstration about how all measurements contain some amount of uncertainty. And the way that we deal with this uncertainty is with significant figures or significant digits, but I mean, usually we stick with significant figures because we then abbreviate it sig figs, and it's got some nice, I don't know, I guess that's alliteration going on. So the first thing that we need to do is figure out when a number is significant or not significant. And then after that, we'll talk about how to carry forward the correct number of significant figures when doing calculations. So this is part one. Is it significant? Which the other way that you'll see this is to ask how many sig figs does this number have? All right, so for the rules, first of all non-zero digits are significant. So for these numbers, we'll look at 28.03 and 0.0540. Get a new color. So 2, 8, and 3 are non-zero, so they are definitely significant. 5 and 4 are non-zero, they're definitely significant. For the zeros, so I guess rule 2, interior zeros are significant. So by interior, we're talking about between two non-zero digits. significant. So in this case, if we were looking at the number 408, and then let's say 7.0301, this 0 is between two non-zero digits. It is significant. This 0 between 7 and 3, this 0 between 3 and 1, all of the zeros in both of these numbers are significant digits. So here's some that are not significant. So I guess rule 3, leading zeros are not significant. So by leading zeros, this means zeros that are to the left of the first non-zero digit. So that sounds weird, but you'll see in the examples, we're talking about when the numbers are really small and you have to do something like 0.0032, right? Those zeros are to the left of numbers that are significant. They're not interior, right? Because there's no non-zero number to the left of that first zero. And let's say 0.000, put in one more for good measure, 6. And let's do this in a different color, say blue. So these zeros are not significant. And these are not significant. Now, this example and the ones that we'll see a little bit later, these are often referred to as placeholder zeros. So these are here just to ensure that the number has the correct value, but they are not significant in terms of the measurement that we were making. If you didn't have them, right, that 3 and the 2 would make a number that is, I don't know, probably much larger than what we have right here, but that's the only reason that they're there. All right, so those are leading zeros. Let's talk about trailing zeros, because we get a few things going on here. So for trailing zeros, so that means to the right, if they are after a decimal point, means that they are significant. So let's look at the number 45.000, and then let's say 3.560. So these 3 zeros at 45.000, they're definitely not placeholders. If we took them away, the number would still have the same value. So it would go from 45 to 45. So the only reason that these are here is because they are significant. So because we also know that the 4 and the 5 are significant, this number has 5 significant figures. For the 3.560, for the same reason, it's not a placeholder. If we took it away, the number would still have the same value. So it's here because it is significant. And we know that 3, 5, and 6 are significant. So this number has 4 significant figures. Okay, so that's after a decimal point. Let's talk about before a decimal and after a non-zero. Before decimal and after a non-zero. These are significant. So let's look at an example for this one. So we're talking about something like 140.00. And we'll say 250.6. So we're talking about this zero specifically, so the 140, because the ones after the decimal point are covered by the previous rule. And now this zero, it's in between non-zero digits, which are always significant, and some zeros that we just said were significant. So this one is also significant. So 140.00 has 5 significant figures. Now this 0 in the 250.6, it's trapped. I mean, even without the decimal point, this would be a significant 0 because it's in between a bunch of non-zero digits, which are significant. But the decimal point here is the kind of the reason this ends up in our example. This is significant, so we have 4 significant figures. So for the first 2 points under rule number 4, it's that decimal point that's making a difference in our significant figures. So let's talk about before an implied decimal point. So really this just means we didn't write the decimal point after the end of a number. So 1200. In the question, I guess we'll use a different color here, of are these 2 zeros significant? It's really unclear. So this is an ambiguous situation. There's no decimal point there, so we don't know if those zeros are considered placeholders, right? It's just giving value to that 1200, or if those are actually significant digits. And think about if this came at the end of a sentence and there was a period at the end of the sentence. Was that period ending the sentence, or is it a decimal point telling you that those 2 zeros are significant? All right, so it's really ambiguous. The way that we avoid doing this, so we're going to say avoid this, is by writing our numbers in scientific notation. So for 1200, if this only had 2 significant digits, we could write this as 1.2 times 10 to the third. And now the only digits that we have to look at are the 1 and the 2. This is how we would write it to indicate 2 significant figures. If we wanted to indicate 3 significant figures, writing 1.20 times 10 to the third. Now I'm looking at this decimal point rule where that 0 is after a decimal. So it is a significant 0. And so this is how I would indicate 3 sig figs. If I wanted to indicate 4, I could write 1.200 times 10 to the third for significant figures. And you can see that they all have the same value. So all of those are different ways of writing 1200. What it's communicating is just a different number of significant figures. Okay, so one other piece that we should talk about before we go into calculations, we need to talk about exact numbers. These are numbers that have no uncertainty, which seems like it wouldn't be possible, but it absolutely is. And they don't affect sig figs in calculations. So they come from a couple of different places. They come from accurate counting. of discrete objects so examples of this, 3 apples, right? If you have 3 apples on the table and you are counting them, there's no uncertainty in the number of apples that you have. If you had the ability, which we do with some fancy equipment, to count atoms, 3 atoms is an accurate counting of discrete objects. And really what this means is that it has an infinite number of significant digits, right? It means 3.000, keep going with the 0, 0, 0, 0, 0, and on and on and on. So we just don't include these numbers. We don't worry about counting sig figs for them. It is tempting to count it as one significant digit, but that will severely limit the way you communicate your answer. So exact numbers have infinite numbers of significant digits. We also don't include conversions and definitions. Which means all of our information about the prefixes won't go in. So 100 centimeters is exactly equal to 1 meter. Neither of those values will affect the sig figs in our calculations. And we also don't worry about numbers in an equation. So let's say you needed to calculate the diameter of something, and you have the radius, right? The diameter is 2 times the radius, but you would not use the number 2 to limit your sig figs in a calculation in any way. Okay, so we know how to count sig figs. We know when we don't need to include sig figs. So let's worry about calculations. Now, a note about calculations is that I will tell you when to do sig figs. So if it does not ask you for a value with the correct number of significant figures, you don't have to carry them forward. It's a good practice depending on what you might need to do in other classes, but I will explicitly ask you to account for significant figures when I want you to do so. Okay, so rules are split based on the type of operation. So multiplication and division go together. And in multiplication and division, the answer has the same number of significant figures as the factor with the fewest number of significant figures. All right, so obviously this is going to be best done with an example. So if we had 1.052 times 12.504 times 0.53, if I just plug this into my calculator, I get 6.7208. And then if I go back through, 1.052 has 4 sig figs. 12.504 has 5 sig figs. And 0.53 has 2. So the answer has the same as the factor with the fewest. So my answer should have 2 sig figs. So I end up with 6.7. So 6.7 is the answer that I would report for this. Okay, so you would end up with the same for division. So if we had, let's just do a quick example for this one, 2.0035 divided by 3.20. Plug it into your calculator, you get 0.626094. This has 5 sig figs. This has 3. So my answer should have 1, 2, 3 sig figs, which means that the answer I report is 0.626. Okay. For addition and subtraction, the rules are a little different. In this case, the answer has the same number of decimal places as the quantity with the fewest decimal places. So it doesn't matter how many sig figs, it matters how many decimal places. So for this reason, you will see addition and subtraction problems written out in a format that you probably haven't seen since maybe, I don't know, elementary or middle school. So if I have a bunch of numbers that I want to add together, you might see it in a column like this. So 2.345 plus 0.07 plus 2.9975. All of these added together, if I just pop this into my calculator, I end up with 5.4125. But in terms of fewest decimal places, this has 3 decimal places. This goes to 2. This goes to 4. So the fewest decimal places is 2, which means my answer should be cut off here. A much easier way to keep track of this, and the reason that it gets put into a column, is that you can just draw a line that separates where you would cut your number off by drawing it after the fewest number of decimal places. So in this case, I would report my answer as 5.41. So another example, let's do 5.9 minus 0.221, and you would get 5.679. We've got 1 decimal place and 3, so my answer will end up with 1, but I can just draw this line in to separate them to help me find the right spot, and this time I would report my answer as 5.7. Okay, so in this last case, I had to do some rounding, and I only want to talk about rounding really quickly. Most of the rules are what you're used to. So if the dropped digit is between 0 and 4, you would round down. The drop digit is between 6 and 9, round up. And you'll see that I left out 5. This one, for reasons to make sure that everything ends up kind of evened out in the end, which I guess is an interesting way to rephrase that. When you have 5 as the dropped digit, sometimes you round down, sometimes you round up, but the only point that you need to remember is to make the answer even, as in an even number, so as in not an odd number. I have examples. So we're going to round each of these to 3 significant figures. And I guess we should label these. So 18.3384, 0.028675, 6.8752, and 92.85. All right. So rounding to 3 significant figures. So my 18.3384, I want to round that to 1 after the decimal place, only because I have 2 before. So that underlined place is the last one I'm going to keep. So the number right after it is how I determine rounding. So just like normal rounding rules. In this case, it's a 3, so I round down. And I get 18.3. For B, those first 2 zeros are not significant because they're leading zeros. So 286 is where I want to round. The dropped digit is a 7, so I need to round up. So 0.0287. Now C, 6.87. That would be my third digit. So my dropped digit is a 5. So my rule here is to make it an even number. So 6.87, since 7 is odd, I do need to round this up and get 6.88. And then in D, 92.8, I'm also dropping a 5. But when I drop the 5, if my charge is to make it even, 92.8 is even, so I leave it. All right, so those are the rounding rules. Guess I should go back up here and label this with 3. So we had 1, multiplication, division, 2, addition, subtraction, 3, rounding, 4 is how you will avoid errors. So to avoid errors in multi-step calculations, do not round until the very end. All right, so I'm going to do one example for this, and I also want to add in here, also, don't forget order of operations. So whichever acronym you have chosen to help you remember PEMDAS, don't forget it, or go look it up and remind yourself, because order of operations will make a huge difference in your significant figures. So our example problem is 6.78 times 5.903 times, in parentheses, 5.489 minus 5.01. All right, so our first step is to deal with the parentheses. And so I'm just going to carry all of this down. We still have 6.78 times 5.903 times, if I do this subtraction in the parentheses, I get 0.479. And this had 2 decimal places. This had 3 decimal places. So my answer will be rounded at 2 decimal places because of subtraction. But I have to carry that number on to do multiplication. So I'm not going to round, but you can see I've put a little underline under the 7. This answer at 2 decimal places is also 2 significant figures. So the 2 sig figs are what will be used in the multiplication rule when it's carried forward. So let's get in. 6.78 has 3 sig figs. 5.903 has 4 sig figs. So if I plug those 3 numbers into my calculator, I get 19.1707. But from my sig fig rules, 2 sig figs is the fewest number of sig figs, and that's the rule I need because this was multiplication. My answer is going to get cut off right here, and my dropped digit is a 1. So my answer will round down to 19.